For decades, we thought we understood spiral galaxies. Every astronomy textbook shows the same simple truth. One galaxy, one core, one supermassive black hole sitting at the center like a cosmic anchor. Andromeda, our nearest large galactic neighbor, should follow the same rule. It's been observed for centuries, photographed by countless telescopes, studied by generations of astronomers who believed they knew its structure inside and out. But in 1992, the Hubble Space Telescope turned its eye toward Andromeda's core and discovered something impossible. Two bright nuclei blazing side by side where only one should exist. The established model shattered in an instant. If you want to understand what this discovery reveals about galactic violence, cosmic collisions, and the terrifying future awaiting both Andromeda and our own Milky Way, hit that like button and subscribe. This is the story of what's really forming at the heart of our neighboring galaxy. Prepare yourselves. Let's begin. Andromeda, catalogue designation Messier 31, sits 2.5 million light-years away. That makes it the closest large spiral galaxy to our own, close enough that it's visible to the naked eye as a faint smudge in the night sky. For centuries, astronomers treated it as a cosmic mirror, a galaxy similar to the Milky Way in structure and behavior. Both are massive spirals. Both contain hundreds of billions of stars. Both should have straightforward, single-point centers dominated by one supermassive black hole. That's the pattern observed in spiral galaxies across the universe. One central engine. One gravitational anchor. The Hubble observation changed everything. When astronomers examined the core in unprecedented detail, they found not one bright point, but two distinct concentrations of light, separated by 5 light-years. 5 light-years might sound small on cosmic scales, but for the nucleus of a galaxy, it's enormous. It's the distance from our Sun to the nearest star system multiplied by more than 1. These two bright regions sat embedded in the very center of Andromeda, shining with the combined luminosity of millions of stars. The immediate question tore through the astrophysics community. Does Andromeda have two supermassive black holes? The possibility was electrifying and terrifying. Binary supermassive black holes exist in theory. When two galaxies merge, their central black holes eventually spiral toward each other, dancing in an ever-tightening gravitational embrace. But catching two such monsters in the final stages before collision should be incredibly rare. The timescales are immense. The physics is brutal. Yet here was Andromeda, apparently hosting exactly that scenario in our cosmic backyard. Follow-up observations across multiple wavelengths began immediately. Radio telescopes, X-ray observatories, infrared instruments all pointed toward Andromeda's core. What they found was both reassuring and disturbing. Only one of the bright spots showed the telltale signs of a supermassive black hole, designated M31 star. This object weighs in at roughly 140 million solar masses. That's more than 30 times the mass of Sagittarius A star, the black hole at the Milky Way's center. M31 star is a genuine monster, feeding quietly on whatever gas and dust. Drift too close to its event horizon, but the second bright spot showed no black hole signature, no radio emissions, no X-ray flares, no accretion disk. It was simply a dense concentration of stars, glowing brightly because so many stellar bodies packed into such a small volume. This should have solved the mystery. Two bright spots, one black hole. Case closed. Yet it opened a darker question. Why does Andromeda's core look like this at all? Normal galactic nuclei don't display this bizarre double-peaked structure. The stars should distribute symmetrically around the black hole, creating one bright central region, not two. The answer emerged slowly over years of detailed analysis. The double nucleus isn't two separate objects. It's an optical illusion created by the geometry of stellar orbits. The black hole sits at one bright spot. The second bright spot is the densest part of an elliptical ring of old red stars, orbiting the black hole in highly eccentric paths. These aren't circular orbits. They're elongated ellipses, stretched and distorted. The stars bunch up at the farthest point from the black hole, creating that second bright concentration. Think of it like a cosmic traffic jam. When cars move on a circular highway, they distribute evenly, but on an elongated oval track, cars slow down at the turns, bunching together at specific points. Andromeda's stars do the same thing, clustering at the apocenter, the farthest point in their elliptical orbits. That clustering creates the illusion of a second nucleus. But this explanation demands another question, one that genuinely terrifies astrophysicists. What could possibly throw stars into such violently eccentric orbits? Normal galactic evolution doesn't produce this pattern. Stars should orbit in relatively circular paths around the central black hole, organized and stable. The eccentric orbits at Andromeda's core scream of trauma. Something catastrophic happened there, something powerful enough to rearrange the orbits of millions of stars in the densest part of the galaxy. The double nucleus isn't just an optical quirk, it's a scar. A fossil of violence written in starlight and gravity, preserved for billions of years at the heart of our neighboring galaxy. What kind of event could create such devastation? The math points toward one horrifying scenario. Andromeda's current supermassive black hole isn't the original. It's the product of a merger, the result of two supermassive black holes colliding and fusing into one. That collision would have been the most energetic event in Andromeda's history, releasing more energy in seconds than entire stars emit in their lifetimes. The true architecture of Andromeda's core reveals itself only through decades of patient observation. Between 1992 and the present day, Hubble has captured hundreds of detailed images of the nucleus, building a three-dimensional map of stellar motion that would have been impossible with single snapshots. Each star in that central region moves with its own velocity, its own trajectory, its own story. By tracking these motions over years, astronomers reconstructed the orbital mechanics that create the double bright spot phenomenon. What they discovered was a structure far stranger than initial observations suggested. The core contains not one, but three distinct stellar populations, each with different ages, compositions, and orbital characteristics. The outermost component is a disk of old red giant stars, roughly several billion years old, distributed in that eccentric elliptical ring. These are the stars responsible for the second bright spot, the one that initially fooled astronomers into thinking a second black hole existed. They orbit M31 star at distances of a few light years, moving in synchronized elliptical paths like a cosmic carousel frozen in slow motion. Inside that red ring sits something completely different, a compact disk of young blue stars. These stars are babies by cosmic standards, only around 200 million years old. They orbit much closer to the black hole, within a light year of its event horizon, spinning in a tight, organized pattern. Their presence is deeply puzzling. Stars shouldn't form that close to a supermassive black hole. The tidal forces and intense radiation should prevent molecular clouds from collapsing into new stellar bodies. Yet there they are, burning bright blue, defying conventional formation models. The spectroscopic analysis tells an even stranger story. When astronomers measured the light from these young stars, they found chemical signatures inconsistent with in situ formation. The metallicity levels, the ratios of heavy elements to hydrogen, don't match what you'd expect from stars born in the galactic center. Instead, they suggest these stars formed elsewhere and were somehow captured or transported to their current position. It's like finding tropical fish swimming in an Arctic ocean. They don't belong there according to any normal process. Then there's the third component, the black hole itself, sitting slightly offset from the geometric center of both stellar populations. M31 star doesn't occupy the exact middle of the red star ring. It sits roughly 1 light-year away from where basic symmetry would predict. This offset is critical. In a normal, undisturbed galactic nucleus, the supermassive black hole should sit at the precise gravitational center, the balance point around which everything else orbits. The displacement of M31 star is another scar, another clue that something violent knocked the system out of equilibrium. Astrophysicists modeled thousands of scenarios trying to explain this tripartite structure. Could normal galactic evolution produce it? Could stellar captures over billions of years gradually create the pattern? Could gas dynamics and differential rotation naturally generate the eccentric ring? Every conventional model failed. The simulations kept producing smooth, circular structures or chaotic random distributions. They couldn't replicate the organized eccentricity, the age segregation, the offset black hole, and the misplaced young stars all at once. Only one class of models succeeded: merger scenarios. When you simulate two supermassive black holes spiraling together and eventually colliding, the aftermath matches what we observe. The collision doesn't just merge the black holes. It fundamentally restructures the entire central region of the galaxy. Stars that were on nice circular orbits get flung into eccentric trajectories. The gravitational waves released during merger are directional, not symmetric, creating a recoil effect that kicks the newly merged black hole away from its original position. Gas clouds get shocked and compressed, potentially triggering bursts of star formation in regions where stars shouldn't normally form. The eccentric ring makes sense in this context. When two black holes merge, stars orbiting near the original black holes don't simply disappear or collide. They get gravitationally scattered, redistributed into new orbital configurations. Computer simulations show that stars initially on circular orbits around two separate black holes will, after merger, find themselves on highly elliptical orbits around the single remnant black hole. The eccentricity is a direct consequence of the violent redistribution of orbital energy during the collision. The young blue stars also fit the merger picture. During galactic collisions, massive amounts of gas get funneled toward the center. This gas becomes compressed, heated, and eventually shocked into forming new generations of stars. These stars form in the churning chaos of the merger, inheriting the chemical signatures of gas from multiple regions of the colliding galaxies. They end up on orbits that would be impossible in a quiescent galactic center, but make perfect sense in a post-collision environment where everything has been violently stirred. The offset position of M31 star clinches the merger interpretation. When two black holes finally coalesce, they emit a burst of gravitational waves. If those waves are emitted asymmetrically, which happens when the two original black holes have different masses or spins, the newly formed black hole receives a gravitational recoil kick. This kick can reach velocities of hundreds of kilometers per second, enough to displace the black hole from the galactic center by several light years. It takes millions of years for the black hole to settle back toward the true gravitational center, slowly spiraling inward through a process called dynamical friction. The displacement we observe in M31 star is consistent with a black hole that received such a kick somewhere between 1 billion and 2 billion years ago. It's still on its way back to the center, still drifting through the stellar population it disrupted. In another few 100 million years, it will reach the true gravitational midpoint and stabilize. But for now, it remains slightly offset, a wanderer in the core it reshaped. Every piece of evidence points toward the same conclusion. Andromeda's strange nucleus is not strange at all. It's normal for a galaxy that experienced a major black hole merger in its recent past. The double appearance, the eccentric stellar orbits, the young stars in impossible locations, the offset black hole, they're all symptoms of the same traumatic event. Andromeda's core isn't forming something new. It's still recovering from something catastrophic that already happened. The eccentric stellar disk at Andromeda's core obeys a counterintuitive rule that baffled astronomers for years. When you track individual stars in their elliptical orbits around M31 star, you notice something bizarre. They don't distribute evenly along their orbital paths. Instead, they cluster dramatically at the apocenter, the point farthest from the black hole. This is the exact opposite of what intuition suggests. You'd expect stars to crowd near the black hole, where gravitational pull is strongest. But physics doesn't care about intuition. The explanation lies in orbital mechanics that Johannes Kepler first described 400 years ago. When an object travels in an elliptical orbit, it moves fastest at periapsis, the closest approach, and slowest at apoapsis, the farthest point. This isn't arbitrary. It's a direct consequence of energy conservation and angular momentum. At periapsis, the orbiting object falls toward the central mass, converting gravitational potential energy into kinetic energy. It screams past at maximum velocity. At apoapsis, it climbs away from the central mass, trading kinetic energy back into potential energy. It slows to a crawl before reversing direction. Apply this principle to thousands of stars orbiting M31 star. Each star spends only a tiny fraction of its orbital period near the black hole, whipping past at velocities of hundreds of kilometers per second. But at the farthest point of the ellipse, each star lingers. It decelerates, pauses, turns around. During that extended loitering time, the probability of finding any individual star at apocenter becomes much higher than finding it at any other point in the orbit. When you observe thousands of stars simultaneously, you see a concentration at the apocenter, creating that second bright spot that initially looked like a duplicate nucleus. This traffic jam effect is mathematically inevitable for elliptical orbits. But the existence of those elliptical orbits is not. That's where the terror begins. In a normal, undisturbed galactic nucleus, stellar orbits should be nearly circular. Stars form from gas clouds that already orbit the galactic center in roughly circular paths. When stars condense from that gas, they inherit those circular orbits. Over billions of years, gravitational interactions between stars can slightly randomize orbits, adding small eccentricities here and there. But the organized, synchronized eccentricity we observe at Andromeda's core cannot arise from gradual stochastic processes. The eccentricity is too uniform, too systematic. Measurements from Hubble and ground-based observatories show that the stellar disk has an average eccentricity of approximately 0.8. In orbital mechanics, eccentricity is a number between 0 and 1. 0 means a perfect circle. 1 means a parabola, an open trajectory that escapes to infinity. 0.8 means these stars travel on severely elongated ellipses, approaching within a light year of the black hole at periapsis and swinging out to 5 or 6 light years at apoapsis. That's not a small perturbation. That's orbital violence. Computer simulations attempting to produce such high eccentricity through normal galactic evolution consistently fail. You can run the simulation for 10 billion years, the age of the universe, and circular orbits remain mostly circular. Minor gravitational kicks from passing stars can increase eccentricity slightly, but they also randomize it. You end up with some stars on mildly elliptical orbits, pointing in random directions. You don't get thousands of stars on highly eccentric orbits, all aligned with the same orbital orientation. The observed pattern at Andromeda's core is coherent. The ellipses point in the same direction. They share a common axis. That coherence screams of a single, powerful event that affected all the stars simultaneously. Only one astrophysical process can deliver that kind of synchronized, large-scale orbital disruption, a major gravitational perturbation caused by a second supermassive black hole passing through the region. When two galaxies merge, their central black holes don't collide immediately. They orbit each other first, spiraling inward over hundreds of millions of years. During this in-spiral phase, the two black holes gravitationally stir the surrounding stellar population like cosmic egg beaters. Stars that orbited one black hole now feel the competing gravitational pull of the second black hole. Their orbits get stretched, twisted, pumped full of eccentricity. The detailed shape of the resulting eccentric disk depends on the mass ratio of the two black holes and the geometry of their final orbits. Simulations show that if two black holes with masses in the range of 50 million to 150 million solar masses merge, they produce eccentric stellar disks nearly identical to what we observe in Andromeda. The agreement isn't approximate, it's precise. The observed eccentricity distribution, the orbital alignment, the radial extent of the disk, everything matches merger models and nothing else. But the most chilling aspect of the eccentric disk isn't just that it exists. It's what it implies about the energy involved in creating it. To pump thousands of solar mass stars into orbits with eccentricity of 0.8 requires adding enormous amounts of orbital energy. Where does that energy come from? It comes from the orbital energy of the two black holes themselves. As the black holes spiral together, they transfer energy to the surrounding stars through a process called three-body interactions. The stars act like a gravitational brake, absorbing energy from the black hole binary and slowing its in-spiral. Calculate the total energy required to eccentricize the observed stellar mass in Andromeda's core, and you get a number around 10 to the 51st power ergs. That's 10 followed by 51 zeros in the centimeter-gram-second unit system. In more comprehensible terms, it's equivalent to converting the entire rest mass of 1,000 suns into pure energy. The two black holes didn't actually lose that much mass, but they did lose that much binding energy from their orbit as they spiraled together. Every time a star got flung into an eccentric orbit, the black holes dropped slightly closer to each other. This energy transfer process is crucial for black hole mergers. Without it, binary black holes would stall at separations of a few light years, never getting close enough to merge. The surrounding stars provide the mechanism that drives the black holes to their final collision. The eccentric disk at Andromeda's core is physical proof that this process occurred. We're not looking at a theoretical model or a computer simulation. We're looking at the actual fossil record of two black holes consuming each other, preserved in the disturbed orbits of millions of stars. The implications extend beyond Andromeda. Every major galaxy in the universe has experienced multiple mergers throughout cosmic history. That means most supermassive black holes are themselves products of previous mergers. The monster at the Milky Way's center, Sagittarius A star, likely formed from multiple smaller black holes that collided and coalesced over billions of years. The universe is filled with merged black holes. Andromeda just happens to be close enough that we can study the aftermath in exquisite detail. The eccentric disk is a warning written in stellar motion. Black holes don't form peacefully. They grow through violence. When two supermassive black holes finally merge after their million-year death spiral, they don't simply fade into each other like drops of water combining. They collide with such violence that the fabric of space-time itself rings like a struck bell. The merger produces gravitational waves, ripples in the geometry of the universe that propagate outward at the speed of light. These aren't gentle undulations. At the moment of collision, the gravitational wave power output exceeds the combined electromagnetic luminosity of every star in the observable universe. For a brief fraction of a second, the merging black holes are the loudest objects in existence, shouting across space-time in a language of pure curvature. Einstein predicted gravitational waves in 1915, but he believed they'd be too weak to ever detect. He was almost right. It took a century of technological development before humanity built instruments sensitive enough to catch them. In September 2015, the LIGO observatories detected gravitational waves from two stellar mass black holes merging over 1 billion light-years away. That detection confirmed Einstein's prediction and opened a new window into the universe. But stellar mass black holes, objects weighing 10 to 100 times the Sun's mass, produce relatively high-frequency gravitational waves that current detectors can observe. Supermassive black holes are different beasts entirely. When objects weighing millions or billions of solar masses merge, they produce gravitational waves with wavelengths measured in light-years and frequencies measured in microhertz, millionths of a cycle per second. These ultra-low frequency waves pass right through Earth-based detectors without registering. To catch them, you need space-based interferometers or pulsar timing arrays that monitor the entire galaxy as one giant detector. Future missions like LISA, the Laser Interferometer Space Antenna, will finally give us the capability to hear supermassive black hole mergers directly. Until then, we study the aftermath. The key feature of gravitational wave emission during black hole merger is asymmetry. If two identical black holes collided head-on with perfect symmetry, the gravitational waves would radiate equally in all directions, carrying away energy but producing no net momentum change. The merged black hole would remain stationary. But perfect symmetry never occurs in nature. Real merging black holes have different masses, different spins, different orbital parameters. That asymmetry breaks the symmetry of gravitational wave emission. More waves radiate in one direction than another. And when you radiate momentum asymmetrically, you get recoil. Think of a rocket engine. Hot gas shoots out one end, and the rocket accelerates in the opposite direction. That's Newton's third law applied to combustion. Gravitational wave recoil works on the same principle. Waves carry momentum. If you emit more momentum in one direction, conservation of momentum demands that you recoil in the opposite direction. The merged black hole gets kicked like a gun firing a bullet, except the bullet is pure space-time curvature, and the recoil velocities can reach thousands of kilometers per second. The mathematics of gravitational wave recoil emerged from numerical relativity simulations performed in the early 2000s. Before that, the equations describing black hole mergers were too complex to solve. Einstein's field equations are 10 coupled, nonlinear partial differential equations involving second derivatives of the space-time metric tensor. Solving them for two moving, spinning black holes requires supercomputers and sophisticated algorithms. When physicists finally cracked the problem and ran the simulations, they discovered recoil velocities far larger than anyone expected. For two black holes of equal mass with anti-aligned spins, pointing in opposite directions, the recoil can exceed 4,000 kilometers per second. That's more than 1% of light speed. At that velocity, the merged black hole would be ejected from most galaxies entirely, flung into intergalactic space like a bullet fired from cosmic violence. Even for more typical mass ratios and spin configurations, recoil velocities of several hundred kilometers per second are common. Those velocities are comparable to galactic escape velocities. The merged black hole doesn't necessarily leave the galaxy, but it does get displaced from the galactic center by hundreds or thousands of light years. The displacement of M31 star from Andromeda's geometric center fits perfectly into this framework. Measurements place the black hole offset by approximately 1 light-year. Using the observed stellar velocities and the mass of M31 star, astrophysicists can estimate how long ago the kick occurred. The black hole is gradually spiraling back toward the true gravitational center through dynamical friction, the process where its motion through surrounding matter creates a gravitational wake that drags it backward. Calculate the friction timescale for an object of M31 star's mass, moving through Andromeda's dense stellar core, and you get between 1 and 2 billion years to drift 1 light year. That timing aligns with other evidence. The eccentric stellar disk shows signs of gradual phase mixing, the process where initially coherent orbital structures slowly randomize over time. The degree of phase mixing observed in Andromeda's core is consistent with an age of 1 to 2 billion years. The young blue stars, formed in the aftermath of the merger, are approximately 200 million years old, which fits the timeline if star formation occurred in a prolonged burst following the initial collision. Everything points to a major black hole merger happening roughly 2 billion years ago. But the recoil didn't just displace the black hole, it also affected the stellar population. When a supermassive black hole suddenly kicks to a new position at hundreds of kilometers per second, the stars orbiting it don't instantly follow. They lag behind, their orbits now centered on where the black hole was, not where it went. Over thousands of years, the gravitational influence of the displaced black hole gradually recenters the orbits, but the process imprints lasting eccentricity. Stars that had circular orbits around the original position now find themselves on elliptical orbits around the displaced black hole. Detailed simulations of this process reproduce the observed properties of Andromeda's eccentric disk remarkably well. Start with 2 black holes, each orbited by circular stellar disks. Let them spiral together and merge with a recoil kick of 300 to 500 kilometers per second. Track the resulting stellar dynamics for 1 billion years. The simulation produces an eccentric stellar ring with properties matching Andromeda's core: average eccentricity around 0.8, aligned orbital axes, enhanced density at apocenter, everything. The match is so precise that it leaves little room for alternative explanations. The gravitational wave burst that kicked M31 star also carried away enormous energy. The total energy radiated during a supermassive black hole merger typically equals several percent of the combined rest mass energy of the two black holes. Calculated using Einstein's famous equation, energy equals mass times the speed of light squared. For two black holes with a combined mass of 140 million solar masses, several percent translates to millions of solar masses worth of pure energy released in seconds. That energy didn't create light or heat in the conventional sense. It warped space-time itself, sending ripples across the cosmos that have been propagating for 2 billion years. Those ripples passed through the Milky Way roughly 2 billion years ago, while Earth was still in the Proterozoic eon, and life consisted mostly of single-celled organisms. The gravitational waves stretched and squeezed our planet by less than the diameter of an atomic nucleus. No geological record preserves their passage. No fossil captures their influence. Yet they carried the signature of one of the most violent events in our galactic neighborhood. A scream of tortured space-time that traversed empty space for 2 billion years before washing over an insignificant rocky world that would, much later, evolve creatures capable of understanding what happened. The kick that displaced M31 star is still in progress. The black hole continues its slow drift back toward Andromeda's gravitational center, plowing through a sea of stars and dark matter. In another billion years, it will settle at the exact midpoint. The eccentric stellar orbits will phase mix into randomness. The young blue stars will age into red giants and eventually die. The visible scars of the merger will fade, leaving only subtle dynamical signatures detectable to sufficiently advanced astronomers. But the event itself, the collision that created M31 star, remains one of the most energetic phenomena in Andromeda's history. The eccentric nucleus isn't the only scar Andromeda carries from its violent past. In 2020, astronomers analyzing data from the Pan-Andromeda Archaeological Survey discovered something massive lurking in the galactic halo. They called it Goliath, and the name fits. It's the fossilized remains of a galaxy that Andromeda completely devoured. Galactic halos are graveyards. When a large galaxy consumes a smaller one, the victim doesn't vanish cleanly. Its stars get stripped away over hundreds of millions of years, stretched into vast streams that wrap around the cannibal galaxy like cosmic spaghetti. These stellar streams preserve chemical and kinematic fingerprints of the destroyed galaxy, allowing astronomers to reconstruct ancient collisions billions of years after they occurred. Andromeda's halo contains dozens of these streams, ghosts of past meals. Goliath dwarfs them all. The Goliath stellar stream spans more than half of Andromeda's visible halo. Tracing it requires identifying individual stars with matching chemistry and velocities across enormous distances. The Pan-STARRS and SPLASH surveys provided the data, measuring spectra and proper motions for hundreds of thousands of stars. When researchers sorted those stars by metallicity and radial velocity, distinct groupings emerged. Most represented small satellite galaxies, dwarf systems weighing millions or tens of millions of solar masses. But one grouping was colossal. The stars belonging to Goliath share remarkably uniform properties. Their iron-to-hydrogen ratios cluster tightly around specific values, indicating formation in a massive, chemically evolved galaxy. Their velocities reveal coherent motion consistent with infall along a specific orbital trajectory. Age dating through main sequence turn-off analysis shows these stars are predominantly 8 to 10 billion years old, ancient even by cosmic standards. Most importantly, their total mass adds up to roughly 5 billion solar masses of stellar material. That's the stellar mass of a galaxy comparable to the Large Magellanic Cloud, the Milky Way's largest satellite. But stellar mass is only part of the picture. Galaxies contain far more dark matter than visible stars. If Goliath's stellar population weighs 5 billion solar masses, its original total mass, including dark matter, probably exceeded 100 billion solar masses. That makes it a giant, not a dwarf. Andromeda didn't snack on a minor satellite. It devoured something approaching 1/3 its own mass at the time of collision. Reconstructing the merger timeline requires dynamical modeling. By running the observed stellar orbits backward in time, astrophysicists can estimate when Goliath first collided with Andromeda. The answer consistently points to approximately 2 billion years ago. Give or take 500 million years. The uncertainty comes from incomplete knowledge of Andromeda's dark matter distribution, which affects orbital trajectories. But the time window is clear. 2 billion years ago, something enormous slammed into Andromeda. The timing is impossible to ignore. The eccentric nucleus formed roughly 2 billion years ago. The gravitational wave kick that displaced M31 star occurred roughly 2 billion years ago. Goliath merged with Andromeda roughly 2 billion years ago. These aren't three separate events. They're one event viewed through three different lenses. When Goliath crashed into Andromeda, it didn't just dump billions of stars into the halo. It brought its own supermassive black hole, probably weighing between 10 million and 50 million solar masses, based on galaxy mass scaling relations. That black hole spiraled toward Andromeda's core, dragged inward by dynamical friction. The journey took hundreds of millions of years. Gas clouds collided and shocked, triggering bursts of star formation. The gravitational disturbance sent ripples through Andromeda's existing stellar disk, heating it and thickening its vertical structure. Finally, after 500 million years of inspiral, the two supermassive black holes met. They orbited each other for millions more years, bound by mutual gravity, gradually losing orbital energy to surrounding stars. The separation shrank from light years to light months to light days. Relativity took over in the final moments. The black holes plunged together, merged, released a tsunami of gravitational waves, and kicked the remnant black hole away from the center. Everything we observe today, the offset position, the eccentric stellar orbits, the young blue stars formed from shocked gas, traces back to that final collision. The Goliath merger explains not just the nucleus but also Andromeda's overall structure. The galaxy's stellar halo is significantly more extended and massive than the Milky Way's. Its disk shows signs of past heating and dynamical disturbance. Its spiral arms contain regions of suppressed and enhanced star formation, patterns consistent with gas dynamics perturbed by a major merger. Andromeda isn't just recovering from the black hole collision at its core. It's recovering from the entire galactic collision that led to that central event. Mergers of this scale are defining moments in galactic evolution. They fundamentally reshape morphology, trigger starbursts, redistribute gas and dust, and reset the central black hole's growth history. For Andromeda, the Goliath merger may have been the most important event in the past 5 billion years. It transformed the galaxy from whatever it was before into the structure we observe today. The eccentric nucleus is just the most visible reminder of that transformation, a bullseye marking the collision's epicenter. And here's the chilling part. Andromeda is about to do it again. In roughly 4 billion years, another massive galaxy will crash into Andromeda with similar violence. That galaxy is us. The Milky Way is Andromeda's next Goliath. Our supermassive black hole, Sagittarius A star, will follow the same path that Goliath's black hole took, a slow inspiral toward Andromeda's core, an eventual merger with M31 star, another gravitational wave burst, another eccentric stellar disk superimposed on the fading remnants of the current one. The cycle of galactic violence continues. M31 star doesn't sit quietly at Andromeda's core. It flickers. Every few months, X-ray telescopes watching the galactic center detect sudden brightening events. Brief flares where the black hole's luminosity spikes by factors of 10 or more before fading back to baseline. These aren't predictable cycles. They're erratic, random, violent bursts that announce themselves without warning and vanish just as quickly. The Chandra X-ray Observatory has monitored M31 star continuously since 2009, accumulating over 15 years of high-resolution data. That dataset reveals a black hole fundamentally different from our own Sagittarius A star. Both are supermassive. Both sit at galactic centers, but their behavior couldn't be more distinct. Sagittarius A star is remarkably calm, emitting steady low-level radiation with only occasional minor flares. M31 star is chaotic, producing irregular bursts that dominate its total energy output. The flares originate from the accretion disk, the swirling maelstrom of superheated gas spiraling toward the event horizon. When fresh material falls into the disk, it releases gravitational potential energy as heat and radiation. The rate of infall determines the brightness. Steady infall produces steady emission. Clumpy, intermittent infall produces flares. The question is, what's feeding M31 star in such an irregular pattern? Normal accretion happens gradually. Interstellar gas drifts toward the galactic center over millions of years, gradually forming a smooth accretion flow. That process should produce relatively constant emission, not wild variability. The flaring behavior observed in M31 star suggests something more dramatic. Material must be arriving in discrete chunks, individual clouds or stellar debris getting torn apart and dumped onto the black hole in concentrated doses. One possibility is tidal disruption events. When a star wanders too close to a supermassive black hole, tidal forces rip it apart. The star gets stretched like taffy, its outer layers stripped away and flung into orbit around the black hole. Half the stellar material escapes, the other half spirals inward, producing a bright flare as it accretes. These events are spectacular but rare, occurring perhaps once per 10,000 years in a typical galaxy. M31 star flares far more frequently than tidal disruptions can explain. The variability timescale is months to years, not millennia. That rules out stars as the primary fuel source. Something else must be delivering gas to the black hole on much shorter timescales. The answer likely involves the eccentric stellar disk itself. Those stars on highly elliptical orbits don't just orbit passively. They gravitationally stir the surrounding gas, creating turbulence and density fluctuations. When a massive star on an eccentric orbit plunges toward periapsis, It sweeps through the inner galactic center like a gravitational bulldozer, pushing gas clouds ahead of it. Those compressed clouds become gravitationally unstable and fragment, with some fragments falling directly toward the black hole. Additionally, stars in the eccentric disk are shedding mass through stellar winds. Old red giants lose significant material from their outer envelopes, expelling gas at rates of 1/10,000,000th to 1/1,000,000th of a solar mass per year. With thousands of red giants crowded within a few light years of M31 star, the collective mass loss creates a substantial reservoir of gas. That gas doesn't fall smoothly onto the black hole. It gets stirred by stellar motions, shocked by orbital crossings, and delivered in irregular pulses. The comparison with Sagittarius A star is instructive. The Milky Way's central black hole sits in a relatively quiescent environment. The surrounding stellar density is lower. The orbits are less eccentric. The gas supply is minimal. Sagittarius A star essentially starves, accreting at a tiny fraction of its maximum possible rate. Its luminosity is so low that it's barely detectable in X-rays. M31 star, in contrast, sits in a disturbed, gas-rich environment still recovering from the Goliath merger. It has abundant fuel and chaotic delivery mechanisms, hence the flares. But there's another, more unsettling possibility. Some astrophysicists propose that M31 star's variability could indicate the presence of a second black hole, a smaller companion still orbiting within the accretion disk. If a black hole weighing millions of solar masses survived the initial merger and remains bound to M31 star, it would periodically plow through the accretion disk during each orbit, disrupting gas flows and triggering flares. This binary scenario is speculative. No direct evidence confirms a second black hole. The flaring pattern doesn't show strict periodicity, which you'd expect from a binary companion, yet the possibility can't be ruled out. Detecting a black hole weighing a few million solar masses orbiting within a few light months of M31 star lies at the edge of current observational capabilities. Future X-ray missions with higher time resolution might reveal periodic modulations in the flares, confirming or refuting the binary hypothesis. What's certain is that M31 star remains in a dynamically active state 2 billion years after the merger that created it. The core hasn't settled into equilibrium. The gas supply remains abundant. The stellar environment continues perturbing accretion flows. Andromeda's nucleus is a laboratory for studying black hole feeding in post-merger galaxies, offering a preview of what the Milky Way's core might look like after our own collision with Andromeda. The flickering isn't random noise. It's the heartbeat of a black hole still digesting the aftermath of cosmic violence. The flares from M31 star raised an obvious question. Where exactly is the fuel coming from? For years, astronomers observed the bursts without understanding the supply chain. Then, in late 2023, combined observations from Hubble and the Spitzer Space Telescope revealed the answer. Long filaments of gas and dust spiral toward the black hole from distances of hundreds of light years, threading through the stellar population like cosmic arteries feeding a hungry heart. These filaments aren't uniform flows. They're structured, turbulent streams showing distinct temperature gradients and chemical compositions. Near-infrared imaging from Spitzer traces the dust, revealing lanes of cool material winding inward. Ultraviolet observations from Hubble capture ionized gas, where starlight heats the filament surfaces. The two wavelengths together paint a complete picture. massive gas rivers flowing from Andromeda's inner disk directly into the central region. The filaments originate in the galactic disk roughly 300 to 500 light-years from the core. At those distances, gas exists in relatively stable orbital clouds, remnants of past star formation episodes mixed with material shed from evolved stars. Normally, this gas would remain in circular orbits indefinitely, slowly mixing with the broader interstellar medium. But Andromeda's disk still carries scars from the Goliath merger. Density waves propagate through the gas, spiral arm structures compress and rarefy the medium, and gravitational perturbations from the asymmetric mass distribution create non-circular motions. When gas clouds lose angular momentum through these perturbations, they begin falling inward. The process isn't smooth. Clouds fragment as they fall, some pieces accreting onto stars along the way, others continuing toward the center. By the time the surviving material reaches within 10 light-years of MR31 star, it's organized into thin filaments following spiral trajectories. These structures resemble water spiraling down a drain, except the drain is a supermassive black hole, and the water is ionized hydrogen plasma. The observed filaments transport approximately 1/10 to 1/100th of a solar mass per year toward the galactic center. That sounds minuscule, but it's enormous by black hole standards. Sagittarius A star accretes less than 1/10,000th of a solar mass per year. M31 star receives 100 to 1,000 times more fuel. Not all the material reaches the event horizon. Much gets blown away by radiation pressure or swept up by stellar winds. But enough survives to power the observed X-ray flares and maintain the black hole's activity level. The filament structure also explains the variability. Gas doesn't flow smoothly down these streams. It clumps and fragments due to gravitational instability and turbulent mixing. Dense clumps travel faster than diffuse gas, creating a staccato delivery pattern. When a particularly massive clump reaches the inner accretion disk, it produces a luminosity spike detectable across millions of light years. Between clumps, the emission drops to baseline. The irregular timing of flares directly reflects the chaotic nature of gas dynamics in the filaments. Spectroscopic analysis of the filament gas reveals another crucial detail. The material is metal-rich, meaning it contains significant amounts of elements heavier than helium. This indicates the gas originated in regions with substantial prior star formation. When massive stars explode as supernovae, they inject heavy elements into the interstellar medium. The gas feeding M31 star shows these enrichment signatures, confirming it comes from Andromeda's disk rather than pristine primordial material falling from the intergalactic medium. The discovery of these filaments transforms our understanding of how supermassive black holes grow in the modern universe. Early in cosmic history, black holes fed on massive gas reservoirs left over from galaxy formation. But in mature galaxies like Andromeda, fuel must be extracted from the existing disk through dynamical processes. The filaments demonstrate that mechanism in action. They're the supply line sustaining M31 star's activity, and by extension, the activity of supermassive black holes throughout the universe. What appears as abstract theory in simulations becomes observable reality in our neighboring galaxy, close enough to study in detail, yet far enough to see the full structure without obstruction. Everything we've discussed so far describes Andromeda's past. The Goliath merger, the black hole collision, the eccentric stellar disk, the feeding filaments. They're all archaeological evidence of events that concluded billions of years ago. But Andromeda's most violent chapter hasn't been written yet. it's approaching at 300 kilometers per second. The Milky Way and Andromeda are on a collision course. Astronomers have known this since the 1950s, when precise measurements of Andromeda's radial velocity revealed its blue shifted, moving toward us rather than away. For decades, uncertainty about Andromeda's tangential motion left the collision timeline ambiguous. Maybe the two galaxies would miss each other, passing within a few 100,000 light-years before separating forever. That hope died in 2012 when Hubble measured Andromeda's proper motion with sufficient precision to calculate the full three-dimensional trajectory. The math is unambiguous. In approximately 4.5 billion years, Andromeda and the Milky Way will interpenetrate. The first passage won't be the end. Galaxies don't collide and bounce. They're mostly empty space, so individual stars rarely hit each other. But the gravitational interaction is catastrophic. Both galaxies will distort, spiral arms shredding into tidal tails, gas clouds colliding and shocking into massive starbursts. After the first passage, gravity will pull the two galaxies back together for a second collision, then a third. Over the course of 1 billion years, multiple collisions will completely scramble both structures, ultimately producing a single massive elliptical galaxy that astronomers have already nicknamed Milkomeda. At the center of this chaos, two supermassive black holes will execute the same death spiral we've reconstructed from Andromeda's nucleus. Sagittarius A star and M31 star will find each other. The process takes time. Initially separated by millions of light-years, they close to hundreds of thousands of light-years after the first galactic collision. Dynamical friction drags them toward the merging galaxy's center. The timescale depends on the surrounding mass density, but simulations consistently show the black holes reaching within a few hundred light-years of each other within 500 million years of the initial galactic collision. At that separation, direct gravitational interaction begins. The two black holes form a bound binary, orbiting their common center of mass. They're still separated by distances that would span dozens of stellar systems in the Milky Way's disk, but they're locked together, falling inexorably inward. Three-body interactions with passing stars extract orbital energy, shrinking the binary. Gas dynamics contribute additional drag. The inspiral accelerates. When the separation drops below 1 light-year, gravitational wave emission becomes significant. Space-based detectors like LISA, if still operating billions of years from now, would detect the binary as a slowly evolving signal, gradually increasing in frequency and amplitude. Over millions of years, the gravitational waves carry away orbital energy faster than stellar interactions can. The binary evolution enters its final phase. Driven purely by general relativity, the last few orbits happen fast. As the black holes spiral from light months to light weeks to light days apart, the orbital velocity approaches a significant fraction of light speed. Gravitational wave emission skyrockets, reaching luminosities that dwarf the electromagnetic output of the entire merged galaxy. The black holes plunge together at relativistic velocities, their event horizons merging in a collision that lasts milliseconds, but releases energy equivalent to several % of their combined rest mass. The gravitational wave burst from this merger will be among the most powerful events in the local universe's history. The waves will carry roughly 3 to 5 million solar masses worth of energy, calculated using energy equals mass times the speed of light squared. That energy propagates outward as space-time curvature, detectable by any sufficiently advanced civilization within a billion light-years. The merger will also produce a recoil kick, displacing the remnant black hole from the center of Andromeda, just as M31 star was displaced after the Goliath merger. Stars orbiting near the black holes during merger will be flung into eccentric orbits, creating a new generation of eccentric stellar disks superimposed on the old structures. If any remnants of Andromeda's current eccentric disk survive the galactic collision, which is unlikely given the violence involved, they'll be mixed with freshly disturbed stars from both galaxies. The resulting nucleus will be even more complex than what we observe in Andromeda today, a palimpsest of multiple merger events layered across billions of years. This future collision isn't speculation. The trajectory is measured, the timeline is calculated, the physics is understood. What terrified astrophysicists about Andromeda's core isn't just what already happened, it's the preview it provides of what's coming for both galaxies. The merger scenario described in the previous section contains a mathematical trap that haunted astrophysicists for decades. It's called the final parsec problem, and it nearly broke the entire theory of supermassive black hole mergers. The problem emerges from the physics governing binary evolution. When two black holes reach a separation of roughly 1 parsec, about 3.26 light-years, the standard mechanisms driving them together suddenly stop working. Dynamical friction relies on gravitational interactions with surrounding stars. As the binary black holes orbit each other, they gravitationally scatter nearby stars, flinging them to higher velocities. Each scattering event extracts energy from the binary orbit, causing the black holes to spiral closer. This process works efficiently when the binary is large and loosely bound, interacting with thousands of stars. But as the separation shrinks, the binary becomes more tightly bound. The orbital velocity increases. The gravitational sphere of influence shrinks. At roughly 1 parsec separation, the binary's orbital velocity exceeds the velocity dispersion of surrounding stars. Stars no longer linger near the binary long enough to extract significant orbital energy. They zip past too quickly for effective scattering. The rate of three-body interactions drops dramatically. Without stellar scattering to remove energy, the inspiral stalls. The black holes remain locked in orbit at 1 parsec separation, circling each other indefinitely without merging. Gravitational wave emission only becomes strong enough to drive the merger at much smaller separations, typically below 1/100th of a parsec. That leaves a gap. Something must carry the black holes from 1 parsec to 1/100th parsec, but the conventional mechanisms don't work in that range, hence the problem. Early calculations suggested that supermassive black hole binaries would simply stall, never completing their merger. Yet observations clearly show that galaxies host single supermassive black holes, not permanent binaries. Merger must somehow happen. The resolution involves mechanisms that weren't included in the original calculations. Gas dynamics provides one solution. If the galactic center contains substantial gas, that gas forms a circumbinary disk orbiting both black holes. Gravitational torques between the binary and the disk transfer angular momentum, causing the gas to spread outward, while the binary spirals inward. This process can bridge the final parsec efficiently, provided enough gas is present. Major galaxy mergers naturally deliver large gas masses to galactic centers, making this mechanism plausible in merger scenarios. Triaxial stellar distributions provide another solution. Early models assumed the stellar distribution around the binary was spherically symmetric. But real galactic centers aren't spheres. They're triaxial, shaped more like ellipsoids with 3 unequal axes. In triaxial potentials, stellar orbits behave differently. Stars can be continuously scattered into the binary's loss cone, the region of phase space where stars pass close enough to interact strongly. This continuous resupply of scattering targets allows dynamical friction to remain effective below 1 parsec. Andromeda's eccentric stellar disk provides observational evidence that the final parsec problem gets solved in nature. The disk exists, which means 2 black holes successfully merged at Andromeda's center, despite the theoretical barriers. The eccentric orbits themselves may hold clues to the solution. When black holes approach 1 parsec separation, while embedded in an existing stellar disk, they don't just scatter individual stars randomly. They reshape the entire disk structure, pumping eccentricity into stellar orbits through resonant interactions. Those eccentric orbits, in turn, affect the binary's subsequent evolution. Stars on highly eccentric orbits spend most of their time at large radii, but make close approaches to the galactic center at periapsis. During those brief close passages, they can interact with the binary even after the spherically averaged density would suggest interactions should cease. The eccentric disk essentially provides a reservoir of stars that periodically dive inward, maintaining scattering rates that wouldn't exist in a circular disk. Recent simulations incorporating realistic gas dynamics, triaxial stellar distributions, and eccentric orbit populations show that the final parsec problem largely disappears. The binary evolution doesn't stall. It proceeds smoothly from parsec scales to millilight-year scales, where gravitational waves take over. The timescale for crossing the final parsec ranges from 10 million to 100 million years, depending on environmental conditions, fast enough that binaries complete their mergers within reasonable galaxy evolution timescales. The fact that Andromeda's nucleus shows clear evidence of a completed merger validates these theoretical solutions. Nature found a way through the final parsec. The mechanisms detailed in simulations aren't just mathematical possibilities. They're physical processes that actually occurred 2 billion years ago in our neighboring galaxy. When Sagittarius A star and M31 star eventually meet, they'll navigate the same challenges and, barring extraordinary circumstances, successfully merge. While astronomers studied Andromeda's ancient merger, a cosmic coincidence delivered a real-time preview of what that merger looked like. In 2023, researchers analyzing archival Hubble data noticed something unusual in the background of Andromeda images. What initially appeared as a single distant galaxy resolved into something far more dramatic. A pair of supermassive black holes in the final stages of merger, photobombing observations of our neighboring galaxy. The system, designated as a background quasar at a redshift indicating it lies several billion light-years beyond Andromeda, shows 2 distinct active galactic nuclei separated by only 300 light-years. That's an extraordinarily small separation for supermassive black holes, placing them deep into the regime where merger becomes inevitable. Spectroscopic follow-up confirmed both objects are genuine black holes, each weighing hundreds of millions of solar masses, locked in a rapidly decaying orbit. The discovery was serendipitous. The observations targeted Andromeda, not background objects. But Hubble's exquisite resolution captured both foreground and background simultaneously. When astronomers processed the images with techniques designed to subtract Andromeda's light and enhance faint background sources, the binary black hole pair emerged. Further analysis using Chandra X-ray data confirmed both nuclei emit X-rays with spectra characteristic of active black hole accretion. What makes this system extraordinary is its evolutionary stage. At 300 light-year separation, the binary has already passed through the regimes dominated by dynamical friction and stellar scattering. It's entering the phase where gas dynamics and gravitational waves take over. Orbital decay calculations suggest the two black holes will merge in somewhere between 350 and 360,000 years. That sounds long by human standards, but it's a blink in cosmic time. This binary is on the verge of collision. The system provides a living laboratory for studying processes that we can only infer from fossils like Andromeda's eccentric disk. Observers can measure the orbital parameters, the gas distribution, the rate of inspiral, all in real time rather than reconstructing them from ancient evidence. Already, the data reveals that both black holes actively accrete gas, producing the bright quasar emission that made them detectable. The accretion isn't symmetric. One nucleus significantly outshines the other, suggesting the two black holes have unequal masses or different accretion geometries. The mass asymmetry has implications for the eventual merger. When black holes of unequal mass collide, they produce stronger gravitational wave recoil than equal mass mergers. The system parameters suggest a mass ratio of roughly 3:1, enough to generate recoil velocities exceeding 500 kilometers per second. After merger, the remnant black hole will be kicked away from the galactic center, just as M31 star was displaced in Andromeda. Future observations centuries from now might detect that displacement, assuming the host galaxy remains observable. Finding such a system randomly in the background of Andromeda images raises a statistical point. If one field contains a close binary, the universe must contain many more. These systems aren't rare, they're just hard to detect. Most merging black hole binaries sit in distant galaxies where even Hubble can't resolve separations of hundreds of light years. The Andromeda background system only became detectable because it's at the perfect distance, far enough that both Andromeda and the background galaxy fit in the same field of view, but close enough that the background galaxy remains bright and resolvable. Upcoming observatories will find more. The James Webb Space Telescope's infrared sensitivity can penetrate dust-obscured galactic centers where optical telescopes fail. The Nancy Grace Roman Space Telescope will survey vast areas of sky with Hubble-quality resolution, inevitably capturing more merging binaries. Each discovery refines our understanding of merger timescales, environmental effects, and ultimate outcomes. The Andromeda background system is just the beginning, but its existence serves a darker purpose in our narrative. It proves that what happened at Andromeda's core 2 billion years ago wasn't a unique event. Supermassive black hole mergers happen throughout the universe. They're standard outcomes of galaxy evolution. The violence, the disruption, the gravitational wave bursts, they're not anomalies. They're typical. Andromeda's scarred nucleus represents the normal state of post-merger galaxies. Our future merger with Andromeda will simply add another scar to the collection, another layer in the palimpsest of cosmic violence. When Andromeda and the Milky Way collide 4.5 billion years from now, Earth will still exist. The Sun will be nearing the end of its main sequence lifetime, swollen and luminous, but still burning. Any civilization present, whether human descendants or something else entirely, will witness the most spectacular astronomical event imaginable. The collision won't threaten Earth directly, but it will fundamentally transform everything beyond our atmosphere. The popular image of galactic collisions involves stars smashing together like billiard balls. That's completely wrong. Galaxies are mostly empty space. The distances between stars vastly exceed stellar diameters. Calculate the probability of direct stellar collision during the Milky Way-Andromeda merger, and you get odds around 1 in several billion. Our Sun will almost certainly not hit another star. Neither will any star in the solar system's neighborhood. But gravitational disruption is inevitable. As the two galaxies interpenetrate, their combined gravitational field becomes chaotic and time-varying. Stars that orbited peacefully in the Milky Way's disk suddenly feel the competing pull of Andromeda's mass. Orbits that were stable for billions of years become unstable in millions. Computer simulations tracking individual stars through the merger show that roughly half get ejected to much larger galactic radii, kicked outward by gravitational slingshot effects. About 20% get thrown out of the merging system entirely, becoming intergalactic wanderers. The solar system's fate depends on luck and initial conditions. If the Sun happens to be near one of the close approach points during galactic collision, it could receive a substantial velocity kick, enough to alter its orbit dramatically. Most simulations show the Sun ending up somewhere in the outer regions of Andromeda, far from the dense central bulge. The orbital radius might increase by a factor of 2 or 3 compared to our current position in the Milky Way. Our new galactic year could last 1 billion years instead of 200 million. The night sky during and after the merger will be unrecognizable. Currently, Andromeda appears as a faint smudge visible to the naked eye under dark skies. As the collision approaches, it will grow, eventually spanning dozens of degrees across the sky, larger than the Moon. During the first close passage, Andromeda's spiral structure will dominate the view, its dust lanes and star-forming regions visible in stunning detail. The merged tidal tails, vast streams of stars pulled out by gravitational interaction, will arc across the entire sky like luminous rivers. Star formation will explode throughout the merging system. Gas clouds from both galaxies collide at velocities of hundreds of kilometers per second, shocking and compressing the material. Compressed gas collapses rapidly, forming massive stars that burn bright and die young. The merger will trigger a starburst epoch lasting tens of millions of years, during which star formation rates exceed normal galactic rates by factors of 10 to 100. The night sky will blaze with young blue stars and the supernovae that follow their brief lives. But these fireworks pose no direct danger to Earth. Even the increased supernova rate doesn't significantly threaten a planetary system unless a supernova occurs within a few tens of light years. The probability of that happening during the merger remains extremely low. The radiation environment in our cosmic neighborhood won't change dramatically. Any life on Earth faces far more immediate threats from the aging Sun, which will begin warming the planet significantly within 1 to 2 billion years, long before the galactic collision. The real transformation happens to our cosmic identity. For 4.5 billion years, Earth has been part of the Milky Way galaxy. That association ends during the merger. Our stellar neighborhood will be scrambled, mixed with stars from Andromeda. The familiar constellations, already slowly changing due to stellar proper motions, will be completely rearranged. If anyone is watching from Earth, they'll see their entire celestial framework dissolve and reform into something unrecognizable. The merged galaxy's center, where M31 star and Sagittarius A star eventually collide, will lie perhaps tens of thousands of light years away, far enough that the black hole merger itself poses no danger. The gravitational waves will pass through the solar system, stretching and squeezing space by imperceptible amounts. No instruments could detect them locally without extraordinary sensitivity. But the aftermath, the eccentric stellar disk forming at the new merged nucleus, will be visible through telescopes as a bright, strangely structured galactic core. Earth survives. Life might survive. But the galaxy we call home will be gone, replaced by something new and violent. The double nucleus at Andromeda's center isn't an anomaly. It's a memoir written in starlight, a permanent record of violence that reshaped an entire galaxy 2 billion years ago. Every eccentric orbit, every displaced star, every flicker of X-rays from M31 star traces back to a collision so powerful it bent space-time itself. What terrifies astrophysicists isn't the violence, it's the inevitability. We've reconstructed the story from forensic evidence scattered across Andromeda's structure. The Goliath merger delivered a massive galaxy and its supermassive black hole. The two black holes spiraled together over hundreds of millions of years, scattering stars and reshaping orbits. They merged in a cataclysm that released more energy in seconds than the stars emit in lifetimes, producing gravitational waves that rippled across the universe and a recoil kick that displaced the remnant black hole from the galactic center. The aftermath still echoes 2 billion years later in eccentric stellar disks, flaring X-ray emission, and gas filaments feeding the displaced black hole. But this isn't ancient history studied for academic interest. It's prophecy. Everything that happened to Andromeda is scheduled to happen to us. The Milky Way and Andromeda approach at 300 kilometers per second. The collision timeline is set. Our supermassive black hole and theirs will follow the same path to merger that created the structures we observe today. The violence that terrifies astrophysicists when they study Andromeda isn't happening somewhere else. It's coming here. Yet there's something profound in this cycle. Galaxies don't die from these collisions. They transform. Andromeda didn't end when Goliath crashed into it. The merger triggered massive star formation, redistributed material, grew the central black hole, and ultimately created the galaxy we observe today. The scars are evidence of survival, not destruction. When Milkomeda forms from our collision with Andromeda, it won't be death. It will be metamorphosis. The universe operates on principles that include violence as a creative force. Stars form in the collapse of shocked gas clouds. Heavy elements essential for life are forged in supernova explosions. Galaxies grow through mergers that temporarily destroy their structure before building something larger. The terror comes from recognizing that we're part of this system, not exempt from it. Our galaxy, our cosmic home for billions of years, is scheduled for transformation just like Andromeda before it. Studying Andromeda's nucleus is like studying our own future. The eccentric stellar disk shows us what stellar orbits look like after black holes merge. The feeding filaments demonstrate how supermassive black holes remain active billions of years post-merger. The gravitational wave recoil explains why merged black holes sit offset from galactic centers. Every detail we observe in Andromeda adds precision to our models of what will happen when our turn comes. Humans have spent millennia wondering about our place in the universe. We built cosmologies that placed Earth at the center, then learned we orbit an ordinary star in an ordinary galaxy. We discovered the universe is vast beyond comprehension, filled with hundreds of billions of galaxies. Now we know those galaxies aren't static monuments. They're dynamic, violent, constantly reshaping through collisions and mergers. We're not watching from outside. We're participants scheduled for the next act. There's beauty in that recognition. The same forces that created Andromeda's strange nucleus will eventually create ours. The gravitational waves that kicked M31 star from its central position will be replicated when our black holes merge. Future astronomers in distant galaxies will observe Milkomeda's core and reconstruct our merger the same way we've reconstructed Andromeda's. The cosmic cycle continues, indifferent to individual galaxies but creating endless variety through its repetitions. What's forming at Andromeda's center isn't something new. It's something old, still unfolding, still visible 2 billion years after the events that created it. The terror astrophysicists feel comes from understanding that this process is universal, inevitable, and already scheduled for our own galaxy. But terror mixed with wonder becomes awe. We're not just studying distant physics, we're reading our own future in the light of a neighboring galaxy, understanding our destiny through the scars left by cosmic violence. In the end, Andromeda's nucleus teaches us that galaxies, like everything in the universe, are temporary structures in constant transformation, and we are privileged to understand what's coming.